Right, so now let's take a recap of the magnetic flux and then flux density. You know, if this is our magnet, if this is our magnet, and this is our north pole, south pole, this is going that way, going that way, going that way. Because this is the direction in which the north pole moves. The direction in which the north pole moves. Okay? Right. So it can also be a current conductor with current I. Okay, and then this, once you do that, the thumb in the direction of the current, our four fingers will be given the direction of the field, the magnetic field around it. Okay? Right, so all these at this point P, at this point P, they will have magnetic flux density. Okay? They'll have magnetic flux density given by density is given by D. Now we know phi is the line. These lines are the flux, okay? We denote by phi, okay? So flux over A is giving us the density that we're talking about. And this density has been found. Or through the work of Biot and Savart, okay, French name, so T not okay. So Biot and Savart, they came to the conclusion. So there is a current conductor. It will have, so far as electrons are moving, okay, they are ordered and they are in a certain direction. So the domains are in the same, are arranged in a certain direction. Therefore, they will have north pole. Just like if you have magnet, if you cut it, you always have what? North pole, south pole. If you cut it, no matter where you cut it, you always have north pole, south pole, because the unit that come together to form the magnet are like that. So there are small units, always north pole, south pole. So when you cut, you always have north pole, south pole. Right. So this from these two people, their work, their work was they found out that, let's assume this is our B. So that is our flux density here. Okay. That's the flux density here, okay, B. Now for a small change, if let's say for a certain reason, and this is due to maybe this length L, okay. Now for a small change in L, we will denote by change in L. It is going to make a small change of what? B here, okay. So let's assume this is our current conductor, okay, with current flowing that way. This the initial length, assume this L, okay. Now it makes this change in L, okay. Now let's say I flow this here, P. Now with respect to this, it was giving us B. So if there's a small change here, L, that L is also going to add a small change B to this point. So the B is the strength of the flux at that point, the strength of the magnetic flux, which is the lines of forces of magnet of the magnet at that point. All right, so that's going to give us change in B. Now they related this, and let's say this angle, you can also make it like that. Okay, let's say this angle is alpha. Okay, that's the angle is substance. Now, if this is a very small change, then this alpha is almost equal to this alpha. Okay, that's what we can say for now. Now, we will continue. So let me draw it well. This is P, point P. Okay, which initially had B, now has increased, and then it has come to, there's a small change in B due to this small change. Okay, now this length was what was actually giving us this B. So this length was giving us B. And this small length is going to give us what? Change in B. Okay? Right, so let's continue and see how we can come to the conclusion very well. Right. So they found out that the change in B was proportional, first of all, to the current that was flowing. The current that was flowing, okay? was also proportional, this change in D was also proportional to the change in L, the new change in L. And this same change in D was proportional to the angle, the sine of the angle, the point mixed with the axis of the current conductor. So that is sine alpha. Okay, and they also made the same conclusion that B was proportional to the distance between the segment that we are interested in and the point P. And it was inversely proportional by the inverse square law. Right. So putting all these together, they came to the conclusion that B was proportional to I changing L sine alpha 1 over R squared. Okay? Now, if we remove the proportionality sign, then we have K, I changing L sine alpha over R squared. Now, K works out to be equal to let me put the K for you. Right, so K was found out to be mu over 4 pi, okay? So that is the permittivity of vacuum, okay, with respect to the magnetic force, okay? K was equal to that, so we can put this in place of K. So this brings us to the equation that we'll be dealing with, okay? The equation that we'll be dealing with. Now let's see how we can use this one to derive the various B's for the for the current conductors, either in the form of a circle, in the form of a straight line, and then in the form of a solenoid. Okay, because if it is a very long distance, then we will call it what? The first point I made, the toroid will be the very long, what do you call it, terms of, what do you call it, the coil, okay? But the solenoid, of course, we have talked about that, that is relatively the one that we will be describing in details. Okay, so let's look at something here. There's one thing about number of turns. Sometimes if it's one number of turns, okay, so we look at what we call the number of turns is given by the number of turns per length. So you have your total length, then the number of turns per that will give you n. So anytime you see n is total number of turns over total length, and that is n. So it's a ratio of the turns per length. Alright, so that factor is there. Let's look at something, how we can use this equation to derive so many other equations. Alright. So, according to Biot Savart, B is proportional, or let's write this straight away, B is equal to R epsilon naught over 4 pi I changing L sine alpha over R squared. Okay. Now let's assume this that is for this change in L at the point R, making a distance an angle phi point P. Okay, that's the general equation. Now let's look at this for a circle. Okay, with a point this radius. The radius being A. Okay, now if it is a circle, then we are interested in this, and then the variable that we have here, we want to find B for at this point, let's say P. We want to find the strength of the magnet, the strength of the magnetic field at P, and that will be due to all the whole length. So first we can do that, we can first find this for a small change L. Okay, then we can sum it up or integrate it over this length. Now, so you will see that we have changed in this beta here. How many variables do we have here? We have 1, 2, 3. Okay, but some of them, in depending on the circumstance, may become constant, and then you can factor them out. So what we are trying to do is you look out for the picture of the question that you are dealing with, and then try to, because this is, you have 3 variables, you can usually integrate 2 variables. Okay, so you try to let one of them, which you know the limits, because if you are going to integrate, you should know the limit. You should let one of them, which you know the limits, be the variable on this side, and then try to get the constant for the other variables, or try to express the other variables in terms of the the one that you want to integrate with respect to. Right, this is what I mean. So in this case, A is here, which is the radius, okay? In other words, let's say R. The distance from this to the segment is R. But you realize that because it's for this circle, R is what? Constant. So R becomes constant. So thank God R is constant. Now let's look at the angle this is going to make. The angle will always be 90 degrees, so that angle is also going to be constant. Then it means this tells you that the formula for this kind of situation will be very simple, very, very straightforward when we call it the answer. Good. So all we need to do is to say that if we integrate this side, change in B, and we integrate, constant will come out. Integrate that side. And integrate that side. You see, this, if you integrate, this is going to give us with respect to B, of course, we are integrating this one with respect to B. Okay, this is going to give us what, and then it's going to give us B. Right, now this side, we should bring all the constants out. So constants. The constants are coming out. R is also a constant. The current flowing through is constant. The change in L is not a constant, so we leave it there. Sine alpha. Alpha is always 90 degrees, so that is also coming out as sine 90 degrees. What about R? R is always constant too, so R is also coming out as a constant, okay? So that we are left with what? L. Okay? And this is why I'm saying that the equation becomes very simple for us to solve. So at this point, B will be equal to what? The constants that we have. Sine 90 is what? Sine 90 is the same as cos 0, which is 1, okay? So it will be, the whole thing will be 1. So that will be 1. So we're going to have this R squared here. Now if we integrate change in L, then we're going to get what? L, okay? If we integrate change in L, we're going to get L, because it is 1, so we're going to get L here. Right, so L becomes the length, okay? But we must give the limit. Now what limit are we saying? If it is, we are starting from here, is 0, and then we go around and come back. We have made what distance? What distance would L be? L will be 2 pi R. Okay? Good. So this is the same as we get L, and then we're going to have from 0 to 2 pi R. Right? So this is it. Now this is going to come out as what? 4 pi R squared. Okay, so this is going to give us 2 pi R. If you put this in the equation, you know we have L, so it will be 2 pi R minus what? 0, which will become 2 pi R. Okay, so that is what we say here. So at the end, pi will cancel pi, 2 go here 1, 2 go here 2. R will cancel, go into 1, R will come here, we'll have only 1 R. So the beta for this one is going to be what? Mu subscript naught subscript naught is equal to, so this is going to be 2, what I mean, have R, anything else, right? I see this ends it, so there's no other variable. I hope you've not left anything, yeah. So we always have to examine, just sure everything is out there. So you don't need to memorize the formulas, just you can go through the processes and then derive them. Now as you do that, the formula itself will stick unconsciously. Okay, right. So that is the formula for this kind of situation. Now let's look at the next kind of scenario. So the point is, you want to integrate this, you want to find B. Now there are so many variables, all the variables, try to get the one that you can find the element. So you see that if it is alpha, we can find if it is the radius, that the length, we can find the limit from 0 to this. So it means we'll let this one be the variable, and then try to, all the other variables, try to see if we can get constant for them, or express them in terms of L. The same thing, then it keeps on going, and you can work out and get your answer. Right. So you realize that this is the formula, but let's assume that we have about n tens of the wire. Then this is for 1. So if you have n tens, then it will be what times n. So b becomes what mu naught pi 2r n. Okay. So that's the final thing. Right. Now let's move on to the next one. The next scenario. So let's see if we have this as our curve. Okay, the center is here. We want to find point P here. We want to see the part of so this is the change of L we are talking about. Now we want to see the change of its magnetic flux here. Okay, we want to see its magnetic flux there. Because this becomes R, so the distance between them. Now we should be able to find, anytime we are finding the force here, B. Okay, initially if it was the length was something like that, it will come with its initial B. Now if there's a change in L, then it's going to add what? Change in B here. But what will happen? The small change that has been added is having what? It flows like that. Okay, so the flow strength is like this. You see that? So that's the angle. Now we always want to find B, that is what, 90 degrees to the point that we are interested in. Okay, so in that case, at this point, we should find the component of this force in the vertical direction, and of course this, because it's a point, the 90 degrees point is also going to be 90 degrees. Okay, the horizontal is also going to make 90 degrees with this point. Okay, so this is the force. You must find the component in the vertical, component in the horizontal. Okay, right. So let's assume the angle this makes with that is the alpha that we're talking about. Okay, you can call that one as alpha. Okay, as alpha. Let this distance here, this distance becomes let's say A. Okay, now let this angle be beta. Okay, it's not B but beta. Okay, this angle be beta. Okay, right. So if this angle is beta, then we can say that this is 90. This angle is 90 degrees. So this will be 90 minus beta. Now remember, this is also 90 degrees. So if here is 90 minus beta, then if this is 90 minus beta and this is also 90 degrees, then here straight away will also be what? Beta. Right. I think this is a very simple thing, because if you look at it from here, this is what you have. Okay, it's going that way. 90. Okay, right. So this whole thing is also 90. So if this is beta and this is 90 minus beta, okay, if you come here and this is 90 minus beta, then this is 90, this is beta, right? So that should be beta. So you can look at it from that angle. Okay, so this line here, that's the length, and then this is going at an angle to it. Okay, let's say that angle is beta. Good. So this is actually chosen as a path between it. Okay, now I want to find the angle this makes with this. So that is the angle it's making. Okay, with this one here. Okay, that's about 90 degrees, because that is the shortest point that we are making. Okay, so we want to see the vertical in terms of vertical, because that is going to give us the vertical axis and then the horizontal axis forces. Okay, right. So the vertical axis forces and the horizontal axis forces. Why we are doing that is So first, it's a false, it will have this and then it will have that, okay? So that at the end we can see if the other forces are going to interact with it, how we're going to have the B there. So this is the picture. This is the picture we have now. Let's make this X, this distance X. Right. Now, what is going to be the problem we are supposed to solve now? We want to find B here. Now, which is varying, okay? The length of this one is fixed, we know, right? We know that, okay? Now, in terms of R, this radius, is it going to change? It's not going to change, so that is also fixed, so that is constant. So we can just more or less it will be the same thing, so which means this is constant. So we now have this and that. Which are we going to use? They are all going to be variables, okay? Change in L is going to span, but it will go through a length here. Now, this is also, but it's fixed, but this is going to be variable throughout, okay? This alpha here, we have here, we can look at it well. Now, is this change in B, okay? Is it just this change in B that we're going to have on P? You realize that change in P is not just going to be this B, because we have components on it, okay? So each component here will be what? Each component here will be cos beta, B cos beta, okay? And then each component here is going to be what? Sine beta and B sine beta. The reason why this is the force, so we have the force like that. It's like this. This angle is beta. So if you want to find its components here, it is what? It is this length and that, which is adjacent and hypotenuse. So it is cos beta is equal to this one B is equal to what? This side, which is the vertical, over this one, which is B. So that the vertical becomes what? B cos beta. And that is why we say this is cos beta. This will be sine beta by using the same principle. Okay? Here becomes beta. So if you want this force here, it is going to be what? Sine. This and that is opposite. So sine beta is equal to what? Opposite. The opposite is the horizontal. Okay, is the horizontal over hypotenuse, which is B. So that H is equal to what? B sine beta. Okay, so this is sine beta there, right? So at this point, what's going to happen is that our beta here actually becomes how is it going to? Let's see how the resultant beta will be. This is on it, this on it. We want to see how effective that will be. So you see that if you go half of this distance, you have a lot of beta cos beta, B cos beta, or up to about half. And then the other half, but this sign will be the same for, if you start from here to this side too, you are going to have below here beta, but that is going to be negative. So you see that this force is going that way, and then that is that way. They are going to cancel out, okay? If they cancel out, it is only this one which will be left. So that this beta that you have there becomes what? B, okay? Right, that's the change in B. Because you are using change in B. This change in B, so this is going to be change in B. Okay, so change in B. The change in B, sine beta becomes the actual B. Okay, so this is what we are saying is equal to this equation. Epsilon naught, mu naught 4 pi I change in L sine alpha over R squared. So this is where we are now. Right, so if we want to find B, out of this, we need to integrate. So we need to integrate this, integrate that, and integrate that. So if we integrate, going to integrate this, this is going to come out as dB sine beta is equal to this. Okay? Alright, but we have already said our dB is given by the change in B is given by this formula, okay? As we said, so it's given by this formula, okay? Let me guess that. We cannot say this is equal to, so we cannot say this is equal to, this has been modified to this, okay? The actual, this is not there. the actual change in beta becomes this, okay? However, we know change in beta when it is not in effect, full effect, it's always given by this as the equation. With all respect, it's always given by this as the equation. So that we're going to put this one for change in b, small b here, okay? So let me put this here. So let me put b here. So this is going to be integrating mu naught 4 pi change in L, or let's make it L sine what? Alpha r squared sine beta. Okay? Right. So what is this going to tell us? So at this point, you realize that r is going to be constant, so it's constant. Okay? Your sine alpha is also going to be constant at every point, so this becomes also constant. So we have a variable here to deal with, the beta. Okay, so your beta, you are looking at it, how it's going to vary. The change in beta is going to vary, or how you're going to look at it from the other perspective. So you realize that all this is a constant, this is a constant, this is a constant, and this is a constant. This is also a constant. Okay, so only d we left. So let's bring all the constants out. Then we're going to have what? We're going to have what? Mu naught 4 pi. Sine. This is the same as 90. It's also going to be 90 all the time. So it's going to be 1. So it's going to be 1. Then we'll have sine beta over r, which is also going to be what? Constant. Okay, r is going to be constant throughout the same distance out. Okay, then we have what? Integrating the L. So this comes out as not sine beta over 4 pi r squared. But let's remember, the L that is going to give us what? L. Then we find the length of L is going to be what? 2 pi, so 2 pi r. We can multiply by n if we have n tens, and then here 0. Okay, right. So if you do that, or before if you do that, remember this r is going to be affected by this. There's going to be a change there. So you're going to have what? Mu naught sine beta over 4 pi r squared. And this is going to be this what? 2 pi r n. So this r will cancel one of this. We have 1 here. This cancels that. This cancels both here. 2. So you're going to have what? Mu naught. So you end up having what? B equal to what? Actual B. So this is the actual B now. Becomes equal to mu naught sine beta n over 2 r. This is it. Okay. Some can also decide to express r in terms of a and x, because they may be given to you. They are given to you. Then you know r squared. This is a term. R squared is equal to a squared plus what? S squared. So just a matter of square root of that, which is r is equal to square root of a squared plus that, and then you can put this one here. So that's it. Once you get this equation, you are good to go. Okay. So when we sum all this up, that's what is going to give us the effective the resultant change in beta, which will be at this point. Okay. Right. Yeah, sorry, just a short thing. I think we made a small error here. Let's see the mistake that we made. When we find 2 pi, this 2 pi r, remember r is not this r. So that's what happened. this R is talking is the radius that we are talking about. So this becomes 2 pi A rather. So 2 pi A. So here will be A. So it means it will not cancel. That means R squared will remain. Okay, R squared will remain. So we'll have R squared here, and then we'll have A. We'll have A here. Okay. Right. So this is how the formula is going to be. We have A there. Okay. So we can express R squared is here. So we can put, since this is R squared, we can put R squared straight away. So that this equation becomes beta. So remember, sorry, this beta that we had is the initial beta which is there, which is always given by this equation. It's always given by this equation. But when it's given to you, you have to find its complements. Okay. So that is why we put it there. We substituted for it as it is. Right. So here it's going to be, because we said R squared is equal to X squared plus A squared, you can put this one there in place here. So they're going to have mu naught sine beta n A over X squared plus A squared. Okay. Right. So this is the final equation that we're having. Okay. You can look at it that way. Right. So these two are the final equations. So from here, if we are told, so this for it, let's say there's another ring here, okay, then we are told to find this, okay. So we now have two rings, okay. So it means this one is going to give us this equation, this is going to give us this equation. Of course, we can. But if let's assume that the distance here to here that we used initially, the distance here is now half, and this is half, so that the distance between them is equal to this, okay. Then in that case, we're going to have the where is it? What do you have here? A is going to be the same, okay, right? A is going to be the same. The distance x, x that we have, x is going to be in this equation is going to have half of x in it, okay. So half of x is going to be that, okay. So that is substituted in the equation, and then you do the multiplications. Sine beta is going to be, how is sine beta going to be? Because we are now having half of that, so we're going to have half of that. So it's just by modifying the equations, okay. Because if you bring it halfway, what will happen? What do you think will happen? This is going to be half x, okay. How is r going to be affected? R is not in the equation, so we are not bothered. So half x is going to be half x. A is the same, okay. Beta, what is beta going to be? Okay. This angle to that angle is coming, so it's more like half of that. And then that goes on and on. You can use that one to substitute and then derive an equation for the Hamilton's, what we call the Helmholtz curve. This is the arrangement is this becomes A becomes, let's say, R. And the distance between them, okay, the distance between them is also R. Okay, the distance between these two is also R. So you see that A will be equal to R, and then S is equal to half R. So we just substitute that, okay? Just substitute that into the equation. Then that will be for one. So that will be for the other one. Of course, if you put them together, you do the rearrangement, you get the final answer. Right. So that is going to be for the so this is R, this is R, okay? And it's curves, okay? That's how it is. Right. So let's move on to the next example. So the Helmholtz curve is like this, something like that. Just for explanation sake, let's say this is R. Okay, this distance between them is also R. Okay, let's say this is the midpoint here. Going to have something like that. So you see that the equation that you had for just one of them at point P, okay, so it's going to be it is like that one you have repeated, so 2 times the equation that you get. By starting with this one, remember x was here, so this is now half x, so r is equal to, so x is equal to r divided by 2, and this is equal to a. So you just substitute them in the equation, and then you get the answer. So this times the whole equation, that gives you the answer. Right. So having done with the Helmholtz coils, we move on to the long solenoids. The long solenoids. The long solenoids. So if we have this solenoid going like that, okay, you can just assume it is this way, and this one is okay. Then we have it like that. So let's say this is point. Now let's say this is the change in L. This is the point P. Okay? Right. So this is more or less like having one coil like that. Okay? So once you get that, you have a point that you're making here. Okay? This is the radius. This we have said is this angle is beta. Okay? Right. So this is beta. Now when there's a change, small change here, this becomes what? Changing like that. Okay? So if you take one coil, the same equation can be used. Let me put the equation so that we can do it. So this was the equation that we derived from this one. Okay, that's the equation. So if we are having this is the coil, this is the solenoid. Okay, if we have magnet inside, we can use it for other purposes, device like the bell, the doorbell, and so on. Now, so this for P for 1. So this is similar to X1. But if we have, let's say, change in L like this, let's say changing. So this one was for the change in L, here. Now we have this length of it. It becomes change in X. Okay. So if this is for one length like that, that is it. Now we have this length, so it is going to go that length. So times what change in X. But remember, we may have a certain number of coils on each one. So times what? Times what? N. Okay, we can make it per 10. Okay, so some also make it N, because we have said N is equal to N over L. Okay, which of them ever you want to put there. Now, so when you do that, you look at the equation. When you have gotten the equation, the parent equation, then you look at what you want. So the point is, the variables that we have here, this distance, remember this is what? Our A. Okay? This is our X. This is the change in X, okay? This is our R's, okay? So you see that the R's are changing. So R is variable here, okay? This is constant. A is going to be constant, so we leave it. Now beta, what's going to happen to beta? Beta is also going to change. Right, so this is changing, okay? This is also a change, okay? N is constant, okay? Or that is infinity, is going to a certain number. So that's it. So how do we get what we want? We look at the variables. Which one? How can we know where R will end? If it is very, very long, we can't tell where R will end. So it's not good to use R for your limits. Now, when you come to beta, beta is an angle. It's starting from here. Let's say it's starting from here at this angle. It will move up to a certain angle. Now, if we stretch this one, it is going to come down like this until it is this way, until this one is also that way. So you see that beta can start from 0, okay, to where 180. You get it? So we can start from, it can come down to this, and it will go up to that. Okay, and so we can get from 0 to 180 degrees. 180 is the same as what? Pi. Right, so it means we can use beta as a limit. So since we are going to use beta, let's make sure that R and what change in X are expressed in terms of what? Beta. And that is where the mathematics comes in. So you see that you have beta here. You try to get r in terms of beta. Try to get change in s. Sorry, change in s. Try to get r in terms of what beta, and change. Try to get what change in s in terms of what beta. Or if you can get them in a to a is a constant, then it will reduce it. Okay. So let's see here. For this small triangle that we have here, it will put this one here. This change, the change here is going to be change in beta. Okay. So you see that change in beta is a small distance here, and this is r. This is going to also going to be another r. Okay. So it's just about using the triangles. Okay, that you can get. There's a relationship between a and beta here. A and beta here. Okay. What about change in x? This is change in x. This is change in x. Okay.